morning everyone. Welcome back for the course Fluid Mechanics. So in my previous video we have discussed about the fluid property, that is capillary action. So today we are going to cover the next property of the fluid, that is bulk modulus and compressibility. So we'll see what is this bulk modulus, so which is the 10th property what we are discussing. So it is denoted by the symbol K. Here bulk modulus is defined as the ratio of compressive stress to the volumetric strain. So simply we can say bulk modulus K is equal to stress divided by strain. So here we'll see what is bulk modulus by considering an example. That is, so we'll consider a cylinder. You can see in the figure, this is a cylinder what we have considered. So where for this cylinder a piston has been fitted. So here, so this is a piston. So this is a piston which is fitted for the cylinder. So here V represents the volume of a fluid so enclosed in the cylinder. So initially the volume of a fluid which is inside the cylinder is denoted as V, where P is the pressure of the fluid when the volume is V. So when the volume of a fluid is V, then pressure is P. So next what we'll do, we'll just apply some force on this piston. So when the fluid of volume V is compressed, we'll compress the fluid by applying some amount of pressure, that is a small amount of pressure, that dP, to the piston. So we'll compress V volume of a fluid by applying some small amount of pressure dP. Then what happens? The fluid volume gets decreased by amount dV. You can see in the figure here. So when you increase a pressure to with a small amount, so initially the pressure was P, so you are applying for that, you are applying some more pressure, that is a small amount of pressure dP. So when the pressure is P, the volume was V. So when you apply a sum of a pressure dP to the piston, so what happens? The volume is going to change. So means there is a compression is happening. So here the dotted line what you are seeing, that indicates the compression of the fluid. When you apply a small amount of pressure dP, then the fluid volume will decrease by a amount, that is d into dV. Okay, so when you apply a small amount of pressure dP, the change in volume occurring is dV. Means we are compressing. What is the bulk modulus definition? It is the ratio of compressive stress to the volumetric strain. So now we have compressed the fluid. We have compressed the fluid, whatever the fluid which is present inside the cylinder, we have compressed it by applying a small amount of pressure, that is dP. So then what happens? Whatever the initial volume V was there, so it is decreased by an amount dV. So that is increase in pressure, so from P to D, P plus dP, and volume is decreased from V to V minus dV. So initially the pressure was P and volume was V. So when you increase or when you apply a small amount of pressure to that initial pressure, it will be P plus dP. So the pressure is increased. When you increase the pressure from P to P plus dP, then what happens? The volume of fluid is compressed or decreased from V to V minus dV. So therefore increase in pressure is what? It is dP, and decrease in volume is dV. So volumetric strain is what? It is a change in length. So we know the definition. The general definition of strain is what? The change in length to original length, or change in volume to original volume. So the change in volume is dV and the original volume is V. So volumetric strain is minus dV divided by V. So since why we have considered this negative sign, since increase in pressure always causes the decrease in volume. So as pressure is increased, then what is happening? The volume is decreasing. So that's why, so as since the pressure increase in pressure always leads to the decrease in volume, so we'll consider negative sign in case of volumetric sign. So that negative sign, what it indicates? That negative sign indicates a decrease in volume. So and that negative sign is used to get a positive value of K. So we are going to use that negative sign, so that, so we'll get the bulk modulus positive value. So now what is the definition of the bulk modulus? It is the compressive stress to the volumetric strain. So compressive stress or stress is nothing but whatever the increase in pressure. So according to the definition, so bulk modulus K is equal to increase of pressure divided by volumetric strain. So increase of pressure is what? It is dP, and volumetric strain is minus dV by V. So here, so what happens? The V will go to the numerator. So the K will be equal to minus dP by dV into V. So and here the unit for the bulk modulus is Newton per meter square. And K, this bulk modulus value of a fluid, is not a constant. As pressure increases, bulk modulus also increases. You can see from this equation, so K is directly proportional to pressure dP. So if pressure increases, then K also increases. So as pressure varies, K is also varies. That's why K is not an constant. And we have the standard values of this bulk modulus for air, water, and mild steel. For air it is 1.03 into 10 per 5 Newton per meter square. For water it is 2.06 into 10 per 9 Newton per meter square. And for mild steel it is 2.06 into 10 per 11 Newton per meter square. So that is the bulk modulus property. The next property is the compressibility. So what is compressibility? All fluids are compressed by the application of external force. So how we are going to compress the fluids? See, by applying some external force, so we can compress all the fluids. And what happens when you apply certain external force? So the fluids will reach to their original volume after the removal of external force. So we know, if for example in the figure you can see here, so this is a fluid which is present. So if you apply some external force, what happens? So the fluid will get compressed. Yes, right, the fluid is going to get compressed. After, if you remove this external force, what happens? So then fluid will go back to its original position. So what is that property? Means it behaves. So that's why from that what we can say is, so fluids also exhibits certain elastic characteristics like elastic solid. So if you apply external force, it will compress, and if you remove that external force, then what happens? It will regain its original shape. So that's why based on that, what we can say, fluids also exhibit certain elastic property like elastic solid. So compressibility can be defined as the reciprocal of bulk modulus, that is compressibility is equal to 1 by K, where K is the bulk modulus. So the definition of the compressibility is reciprocal of It is the reciprocal of bulk modulus. See here, you have set some of the examples of this compressibility. Injection of air. So that is also one of the example of compressibility. The next property of the fluid is vapor pressure of a liquid. So what is this vapor pressure? First of all, what is vaporization? See, whatever the liquids which are present, all the liquids has a tendency to vaporize or evaporate. So we know water, milk, petrol, diesel, anything, any liquid has a capacity to vaporize or evaporate. So, what is vaporize or what is evaporation or vaporization means it is a change from liquid to gaseous state. The change of liquid state to gaseous state is called the vaporization. So, all the liquid has a capacity to vaporize. So the process where liquid molecules on the surface escapes in the form of vapor. So is called vaporization. So what is vaporization is? It is a process where the liquid molecules on the surface, see this is the surface, okay? So where from this surface, so all the liquid molecules start escaping. So that process is called vaporization. And here vaporization occurs by one is increasing the temperature to its boiling point and by decreasing pressure above the surface of the liquid to a value less than vapor pressure of the liquid. So from these two, so the vaporization will occur. So that is when you increase the temperature or when you decrease the pressure. So from those two cases, the vaporization is going to occur. And here, so to explain what is this vapor pressure, see, we'll consider, so we'll take a closed vessel here in the second figure, what you're seeing. So we'll figure 1. So we'll consider a liquid inside a closed vessel. Okay. So, and what happens? So when the liquid is confined in a closed vessel, and when you start boiling this water or when you start boiling this liquid which is present inside the closed vessel, so the deposition of vapor molecules is going to happen. See here the, so whatever the space between the top lid and the liquid surface. So between that space, the deposition of vapor molecules, once you increase the temperature or once you start boiling the liquid, so what happens? The changes, the liquid molecules will change to a gaseous molecules, and those gaseous molecules will deposit in between the space available between this top lid and the top surface of the liquid. Okay, and whatever those vapors present in between the space, so these vapors will exert a pressure on this surface, so that pressure is called vapor pressure. So vapor pressure is nothing but it is a pressure exerted by the vapors of the liquid, so which is present between the space, so available between the top lid and the water surface. So vapor pressure is nothing but vapors exert a partial pressure on the liquid surface. That partial pressure is known as the vapor pressure. So and that pressure, so whatever the vapor pressure which is exerted by these vapors, so that will increase with the temperature. We know if you go on increase the temperature, all the liquid molecules will go on convert into gaseous molecules. So that's why if you increase the temperature, so if the vapors, the change of liquid state to gaseous state happens, so the more and more vapors will generate. So if the vapors density increases, then what happens? So the vapor pressure also, whatever the pressure which is exerted by the vapors will also increase. So that's why if the temperature increases, as then the vapor pressure also increases, because if the temperature increases, what happens? Molecular activity is going to increase, which in turn increase the vapor pressure. And if the external absolute pressure imposed on a liquid, so this is the first case how the vapor pressure is going to develop. The second case is when you decrease the pressure, so less than the vapor pressure above the top surface. So if the external absolute pressure imposed on a liquid so is reduced to an extent that is less than vapor pressure. For example, see here in the figure you can see, so this is an atmospheric pressure and this is an vapor pressure. So this, whatever this atmospheric pressure is there, we'll consider that as an external absolute pressure. So we are imposing this external absolute pressure so on the surface, okay, on this liquid surface. So and if, for example, this atmospheric pressure is less than the vapor pressure, so then what happens? Then the vaporization will occur. So that is, boiling occurs whatever be the temperature. Even though after some time, for example, so if you consider, so you are boiling the water, okay, you are boiling and water, and it has been reached boiling point, so which is 100 degrees Celsius or 1000 degrees Celsius, anything. Okay, so after the boiling point also, after it reaches boiling point, so even if you switched off the gas, for example, you are boiling a water in a gas, so after it reaches a certain point, even though if you switched off the gas, what happens? So the water will still keep on boiling. Okay, so that is, so the boiling occurs whatever be the temperature, even though the temperature means, so you have stopped boiling, you have stopped or switched off the gas, so still boiling will goes on occurs, and thus liquid may boil even at ordinary temperature. Okay, so even though, so after the boiling point has been reached, so even though the temperature is less, whatever be the temperature, so the boiling is still go on occurs. For example, here we'll consider how the vaporization occurs. So as you see in the figure, so we'll consider any flow system. This is a flow system, and pressure at any point in a liquid is equal to the vapor pressure. For example, if you consider any point, so at that point, the pressure is what? It is a vapor pressure. And if the pressure is equal to vapor pressure, what happens? So if you consider at any point, if the pressure is equal to vapor pressure, then only vaporization will occur. Okay, and that will result, that vaporization results in what? So packets of dissolved gases and vapors. It will, so once the vaporization occurs, it will generate a packets of dissolved gases or vapors. So these are the vapors what you are seeing, like bubbles. So those are the vapors. So what happens if you consider any flow system, and if you reduce that pressure to a vapor pressure, what happens? The vaporization is going to occur, and that will result in the generation or result in the packets of dissolved gases or vapors, and the bubble of vapor carried to a higher pressure. So what happens? So it is a flow system. Okay, so it is flowing. So once after the generation of these vapors, so whatever this flow is occurring, so these bubbles will be carried by this flowing water. These bubbles will be carried by this flowing water to a higher pressure region. So from a lower pressure region, so these bubbles are carried to a higher pressure region. So while carrying, what happens? While these bubbles are moving, the collision of a bubble is going to occur. So one bubble will collide, or one vapor will collide with other. So due to that, what happens? The collision of the bubble will occur, and so due to that collision, what happens? High impact pressure is going to generate. So high impact on this material or in on this flow system is going to occur. So due to that collision, what happens? High impact pressure is going to generate, and that impact pressure, due to that high impact pressure, what happens? So the material on the boundaries erode. So whatever this boundary is there, so or this boundary, so the material of this boundary will erode due to this high impact pressure. Okay, and when the material gets eroded, when this material gets eroded, what happens? So that will lead to the formation of cavities, like how the cavities is going to form inside your teeth. So similarly, so on this material of any flow system, so these cavities is going to form, that is known as the, that phenomenon is known as a cavitation. And here, so mercury will be having a very low high pressure, so that's why it has an excellent fluid, so to use in barometer. Okay, so hence mercury, as mercury has a very low vapor pressure, it is used in barometer, so which is used to measure the vapor pressure. And volatile liquids like benzene, so will be having high vapor pressure. See, this is a cavitation, how it is going to occur. So this you can see in case of turbines, and here also you can see how the erosion of the material has been occurred. So like this. So this is a cavitation, the erosion of the material due to the high impact pressure, which is going to generate due to the collision of the vapors. Okay, so where the generation of vapor pressure occurs when the pressure is equal to vapor pressure. So that process is known as the cavitation process, and in the figures you can see how this cavitation will occur. So just you can imagine how the cavitation is going to occur in your teeth. Similarly, so for any flow system, so the cavitation will occur, so due to the low vapor pressure. So the next you have classification of fluids. So we have different types of fluids as you see the flow chart. So we have classified the fluids into different classification. So one is ideal fluid, real, ideal plastic, compressible and incompressible, Newtonian and non-Newtonian. So these are the different types of fluids. So we'll see one by one what is ideal, what is real fluids. So first of all, the first fluid type of fluid is the ideal fluid. So what is ideal fluid means? See, these are the fluids which are incompressible, or when there is no viscosity and no surface tension. So where all the properties are zero. So that fluid is called the ideal fluid. Okay. So ideal fluid is nothing but it is a fluid. So where in, it is the fluid is incompressible, which means the K value is 0, and mu, the viscosity is 0, and no surface tension, sigma is 0. Okay, it is, these are the fluids with no properties, or so whatever the fluids which will be having a 0 viscosity, so those are called ideal fluids. And these are imaginary fluids. These are just an imaginary fluids, so where it does not exist. So for all the fluids, we will be having certain viscosity value, surface tension value, and all the fluids can be compressed. Okay, so that's why these ideal fluids aren't just an imaginary fluids which does not exist in nature. And this why where we are going to use this concept of ideal fluid means, so for the analysis of fluids, to simplify the mathematical analysis, to to solve the problem in a simple way, or to analyze, to do the analysis of fluids in a simple way, So we are going to assume the fluid as an ideal fluid. So for example, water, usually water is considered as an ideal fluid. The next type of fluid is a real fluid. See, it is an opposite of ideal fluid. So these are the fluids which possesses viscosity, surface tension and compressibility. And whatever the fluids which exist in the nature, all are real fluids. It may be water, milk, honey, petrol. All the fluids are real fluids. And after that, see, we are going to classify the types of fluids based on the Newton's law of viscosity. So, and that based on that Newton's law of viscosity, whatever the fluids which we are going to classify, so that is called the rheology of a fluids, or so a rheology diagram of the fluids will say. So here the fluids like air, water, glycerin, kerosene, so all those fluids will follow this Newton's law of viscosity. According to this Newton's law of viscosity, so we'll classify the fluids as the Newtonian fluids, non-Newtonian fluids, ideal plastic, and thixotropic fluids. So here we have this rheology diagram to explain the different types of fluids based on the Newton's law of viscosity. So here in the figure you can see the x-axis indicates the velocity gradient and the y-axis indicates the shear stress, because we know the Newton's law of viscosity is shear stress is directly proportional to rate of shear strain, that is du by dy. So tau is the shear stress and du by dy is the velocity gradient or shear strain. So x-axis represents du by dy and y-axis represents shear stress. So here you can see the linear graph. This is a Newtonian fluid, this is non-Newtonian fluid, and this is a ideal plastic, and this is a thixotropic fluid. So most of the engineers deal with the Newtonian fluids. If we consider all the different types of fluids, all the engineers, so most of the engineers, so we are going to deal with this Newtonian fluids. And the study of this non-Newtonian fluids is called the rheology. So the study of non-Newtonian fluids is called the rheology of the fluids. So we'll see what is Newtonian fluid now. See, if the fluids obeys Newton's law of viscosity, then that type of fluid is called the Newtonian fluids. So what is Newtonian fluid? It is a real fluid in which shear stress is directly proportional to the rate of shear strain. So if tau is directly proportional to du by dy, then that is called Newtonian fluids, or in a simple term what we can say, so the fluids which obeys Newton's law of viscosity is called Newtonian fluids. So where the Newton's law of viscosity is tau is equal to mu into du by dy. So this and this whatever the Newton's law of viscosity is there, that is tau is equal to mu into du by dy. So there is a linear relationship, as the definition indicates, that is shear stress is directly proportional to shear strain or velocity gradient. So there is a linear relationship exists between this shear stress and velocity gradient. See, the examples for this Newtonian fluids is, one is glycerin and the kerosene, water are the Newtonian fluids. See this linear relationship, you can see the linear line. So that represents the Newtonian fluids, because so it velocity gradient is shear stress is directly proportional to velocity gradient, or velocity is directly proportional to shear strain. So where it represents the linear curve. The next is non-Newtonian fluids. So what is this non-Newtonian fluids? See here, The fluids which does not obey Newton's law of viscosity, so those are called non-Newtonian fluids. Which does not obey the Newton's law of viscosity, those are called the non-Newtonian fluids. So, or the definition we can say it is a real fluid, so in which the shear stress is not proportional to the velocity gradient. So there is no linear relationship. Here there is a non-linear relationship. So non-Newtonian fluids means it is a real fluids in which shear stress is not proportional. Means tau is not proportional to du by dy, or it does not obey Newton's law of viscosity, and there is no linear relationship, but there is a non-linear relationship between tau and velocity gradient, where you can see the green color or whatever I am indicating now, so blue color, so that represents a non-Newtonian fluid where it is the curve is not a linear curve, so it is a non-linear relationship. So the examples for this non-Newtonian fluids are so blood and molten rubber and polymer solutions. So those are the example for non-Newtonian fluids. So the next type of fluid is an ideal plastic fluid. See, these are also called as the Bingham plastic. So ideal plastic fluids are also called as Bingham plastic. So these are the types of non-Newtonian fluids. So ideal plastic fluid is a type of non-Newtonian fluid. So where there is a linear relationship exists beyond the yield stress. For example, see here this is a yield stress. So at this, after certain a point of stress, so what happens? These fluids will exist. So after certain stress, after applying some of the stress, so then the linear relationship is going to exist. So that is called the ideal plastic fluids, where shear stress is more than the yield value. So here, after certain yield stress, the linear relationship is going to exist, and this yield stress is less than the shear stress. Shear stress is more than this yield value. The example for this ideal plastic fluids are the paints, what you are using for painting, drawings, and your ketchup and the toothpaste. So those are an ideal plastic fluids. So the last type of fluid is a thixotropic fluid. So where this is also one of the type of non-Newtonian fluids. So here, so this ideal plastic fluids exist a linear relationship after certain yield stress. So here, in case of thixotropic fluids, so it exhibit a non-linear relationship. So after the initial yield stress, so that's it. So here, so after a yield stress, the fluids will exhibit non-linear relationship. Those fluids are called thixotropic fluids. So the example for this thixotropic fluids are the inks, what you are used to print for the printing inks. So those are the examples for this thixotropic fluids. And the next type of fluids are compressible and incompressible fluids. So if the fluids changes its volume by application of certain pressure and temperature, then those are called the compressible fluids. So if you vary or if you increase or decrease both temperature and pressure, if the volume of the fluid changes, then those are called compressible. So if the volume does not change, if the volume does not change its if the fluid does not change its volume, so by the application of pressure and temperature, so then those are called the incompressible fluids. So these are the different types of fluids based on the Newton's law of viscosity, and which is known as the rheology of the fluids. So stop it here and we'll just continue with the next topic in the next class. Thank you.